Alright, so in this lecture we're gonna discuss how to work with the vectors, because as we have seen last time, velocity and acceleration, they're both vectors, and also forces and momentum we're gonna discuss later. They're all vectors. They have both magnitude and directions. So working with them, it's not going to be intuitive. You don't just add them and subtract them. We're like working with scalars. So that's why we want to spend some time discussing how to work with vectors. So take a look at slide 10. A vector, as I said, a vector has both magnitude and direction. When we draw a vector, right, we need to draw an arrow with the tip representing the direction of this vector. Right. And then how do we represent the magnitude and direction of this vector precisely? Okay, so if I have a vector, I draw it in a coordinate system. I set up like this, x and y, right? And there's a vector starting from this point. I call this point origin, right? How do I represent this vector, okay, precisely, right? Well, there are two ways to do that, okay? One way is that because it has a magnitude and direction, I would just use two numbers to represent the magnitude and direction, right? So the magnitude is usually the length, right? It's just the length of this vector, so we call it r. So you can measure the length of this vector, so that's going to be the magnitude, right? And the direction, right, is a little bit tricky, okay? In physics, we don't normally use words to describe it, okay? Because it's not that precise, okay? If you say upright, okay, this is upright, this is also upright, this is also upright. Which one do you mean, right? Okay? So we would usually pick a reference axis and then use an angle between this vector and this reference axis to represent the direction of this vector. For example, usually if this is a vector and I set up coordinate system this way, I pick this end of this vector as the origin. So I would just pick, usually people would pick the angle between this vector and the positive x-axis to represent its direction, to specify its direction, right? For example, if I say the r is gonna be 3 meters, right? R is gonna be like 5 meters, theta angle is 40 degrees, right? If I tell you these two numbers, you know all the information about this vector very precisely, right? The length, the magnitude, 5 meters, the angle, the direction, okay, it makes angle 40 degrees with the positive x-axis, okay? So that's one way we can represent vector. Another way is the component form, okay? So if I projected this vector onto x direction, right, I would find a number here, okay? Say this is 4 meters. And then I can also project it onto the y-axis, right? So I would also get a y-coordinate here, say 3 meters, right? So if I tell you the x and y coordinates of this vector, you also know all the information of this vector. You can also draw this vector, right? You're going to draw a very unique vector if I tell you these two numbers, right? All you need to do is just find this x coordinate, find this y coordinate, and then draw a vector that has these two components. And there's always one unique way to draw that vector if I give you these two components, okay? So that's another way to represent a vector. That's called component form, okay? And we're going to see this is the form we're going to use most of the time when we deal with vectors, because it's very, very useful, very powerful. It's going to help us work with these vectors, okay, very easily, okay? So then there will be a relation between these x and y components, right? And this magnitude and this theta angle, right? So if you use this right triangle right here, you see that if I pick this right triangle, okay? Then obviously if I have the r and theta, I can find this x and y, right? Because the x is just gonna be this side of this right triangle, right? And y is this side. So this is going to be the x component, this is going to be y component. So if you use this right triangle, you can find that x is going to be r times cosine theta, right? Because this is theta angle, this is adjacent to the theta angle, so adjacent over hypotenuse is going to be cosine theta. You rearrange that, you can find x if you know r and theta. And then y, what about y? Well, y is this side, which is also equal to this side, right? How do you find this side in this right triangle? This side is opposite to theta angle, right? So you would have y over r equals sine theta. So you rearrange this equation, you get y equals r sine theta. So that's how you find the components. If I tell you the magnitude and the direction of this vector with an angle, right? And then you can do things backwards, right? If I tell you the x and y components, you can also find the magnitude and direction of this vector. So say if I give you x and y, how do you find the magnitude? Well, that's just going to be the hypotenuse of this right triangle. If you give me these two sides, so I would just do x squared plus y squared and square root. If you want me to find the magnitude of these two guys given these two components. What about the direction? Again, direction, you're going to pick a reference axis and then you just draw the angle and calculate the angle between the vector and the reference axis. Then I know the direction precisely, okay? So in this case, if I have this vector, I draw the x-axis horizontal, y-axis vertical. The theta angle, if I know x and y, it's going to be tangent inverse this side over this side, because tangent is opposite over adjacent, right? So we do use a lot of trick in this class, okay? You definitely be very good at trick if you want to work with vectors, okay? So that's a relation between these two representations, okay? You can either go from r theta to x and y or xy to r theta, very easy, okay? So, and then what I usually tell my students is this: don't remember these four equations. A lot of people, again, I have to emphasize many times, physics, it's not about memorizing equations. On the test, you will get all the fundamental equations you need. You don't need to memorize them, but you need to know how to manipulate them, how to do the math, okay? How to apply the theories we learn in this class in a real problem. That's what we're learning in physics. We're not learning memorizing stuff, okay? So what you should do, take a look at the next slide. You don't remember these equations. What you should do, just draw this diagram, draw all these lines, and then use the right triangle, okay, to help you figure out things you need, okay? And especially don't do this. A lot of people, they were like, I've seen x equals r times cosine theta. I'm going to always remember that. Every time I want to find x component, I will just pick this magnitude from this problem, pick this angle from the problem. I'm going to do magnitude times this cosine theta angle. It totally depends what angle you're talking about, right? It can be sine, it can be cosine, okay? Don't always remember these shortcuts, okay? These shortcuts can be only true for some certain problems, okay? It's not a universal law that x component is always going to be a cosine theta angle given in the problem, okay? Don't do that. That's not what we're learning in physics. We're not learning to memorize shortcuts, okay, from a certain type of a problem, so that next time we see a similar problem, I'm just going to use the shortcut and plug numbers in. No. What we're learning here is this. if I want to go from r theta to x and y, or from xy to r theta, all I need to do, just draw out these components, draw out this vector, draw out this angle, and then use the right triangle, use trig. I should be able to figure out everything, okay? That's the right way to do that, right? I don't need to remember these equations, I don't, okay? If you know how to do trig, okay? If you are familiar with, you know how to work with sine, cosine, the Pythagorean theorem, okay? You know how to find them, okay? You can know how to find things you need. That's what we're learning in physics, okay? Okay, so that's the two different representations of vectors. And then if we want to work with vectors, okay, we need to set some rules for vectors, okay? So these rules are not like intuitive, okay? Not all the rules are intuitive because we're dealing with some mathematical concepts, okay? So we have to set some rules. So let's take a look at these rules for vectors, okay? They're gonna help us work with the vectors, like add them, subtract them, multiply them, okay? They are different from numbers, so these rules may not be that intuitive. So first rule is the equality of two vectors. So we're gonna consider two vectors are equal if they have the same magnitude and same direction. So the starting point doesn't matter if we are manipulating vectors, okay? So this is totally mathematical. This is totally mathematical, okay? So for example, take a look at all these vectors we draw on slide 12. All these four vectors, they have the same magnitude, the same length. They're all pointing in the same direction. So I would say they are all equal mathematically, okay? If I want to manipulate with them, each of them is going to be the same to me, okay? So this allows us to move a vector parallel to itself without changing that. And that's going to be very useful when we add vectors, subtract vectors, multiply vectors, okay? So that's why we set this rule. Now the second rule, then how do we add vectors? How do we add vectors, okay? If you want to add two vectors, this is a rule, okay? You're going to do that pictorially. Say if I have a vector A like this, and this direction has this magnitude, I have another vector B, okay, with this length and this direction, and I want to add these two vectors, okay? You add two vectors, it's different than adding two numbers, okay? How do I add these two vectors? When you add these two vectors, you still get a new vector, okay? And then the new vector is going to be having this magnitude and this direction. How do you find this new vector? You draw this A vector. Now you can parallel move this B vector. So that's why we're going to set up the equality of these vectors. You're going to move this to B vector, okay, parallel to the tip of A, okay? Then you're going to draw B again. Okay, so you're just only moving it parallel, so you're not changing this B vector. So they're still the same length, pointing in the same direction, right? Now you're going to connect this end of this vector, okay? The starting point of this vector A to the end point, the tip of vector B. So you're going to connect these two lines using the 2 points using a straight line. And this vector is the sum of these two vectors, right? So again, this is not intuitive at all, right? Because we don't deal with vectors in our life a lot, okay? So that's why we want to set some rules when we deal them mathematically, okay? Otherwise, it's going to be a chaos. You don't know how to work with them. So that's called a head-tail method. So that's how you draw the sum between two vectors pictorially. And of course, if you have C, D, you have more than two vectors, you just repeat the same process until you have all these vectors included, right? Say if you have a C vector, you want to add C to A and B, you're going to draw it from this point, right? So take a look at the image on this slide. And then if you have another vector, the fourth vector, then you draw the fourth vector starting from the tip of the third vector. Until you have done this with all the vectors you want to add, You connect the very beginning of the first vector to the very end of the last vector. That vector, that new arrow you draw, it's going to be a sum of these vectors. So that's how we add 4 vectors. Okay, so that's a rule. Now, so you would say, if I want to add like A to B to C to D, do I have to always follow this order? What if I do A plus C plus D plus B? Is it different than I do A plus B plus C plus D? Okay, actually there's no difference. Okay, you can repeat this process if you do A plus B, or if you draw B first, okay, and then you draw A, again you will get the same vector. Okay, so it's going to be in the same direction. Okay, well, if they don't look the same, it's my drawing. Okay, the theory is still true. So you see that, so that means the 2 vectors, if you add vectors together, they are commutative. Okay, so you add A to B or you add 2B to A, use the same method, you will get the same vector. Okay, so the sum of these, the addition of 2 vectors is commutative. Okay, it's commutative, I'm sorry. Okay, so that's a little bit intuitive. That's like adding 2 numbers, right? If you add 2 numbers, you add 2 to 3 or 3 to 2, you get the same number. Okay, and then you can also, when you add like 3 or 4 vectors together, okay, you can add them any order you like, and then you can try that. You can draw these vectors, okay, according to based on any order you pick, you always get the same vector. So there's always associative law of addition for vectors, and that's also a little bit intuitive because it's like adding numbers, right? If you add 3 or 4 numbers together, it doesn't matter the order you add them, you always get the same answer. Okay, so these 2 laws, they are intuitive. Okay, they are the same as the laws for adding numbers. Okay, then sometimes we want to subtract 2 vectors. Okay, how do we do that? Well, in fact, you don't need to make another new rule to subtract 2 vectors, because if you want to do A minus B, okay, in this case, all you need to do is just use this fact that A minus B equals A plus negative B, right? So that's how we do, like, how you subtract 2 numbers. That's true for numbers, right? So if I have A and B like that, and I want to find A minus B, so all I need to do is just do A plus another vector I call negative B, right? And then how do you draw negative B? Negative B is defined as a vector with the same length of B but in the opposite direction. Okay, so that's intuitive, right? That's intuitive. That's how you make a negative vector. Okay, so in this case, if you want to do negative B, you're going to draw it this way. Okay, hope it looks like negative B. And then you're going to connect these 2 vectors. So this is another new vector. You're just adding these 2 vectors together. Right? So that's going to be equal to A minus B, because it's just A plus negative B. I'm still using the rule for addition, but now I'm just adding A and negative B. So I don't need a new rule to subtract 2 vectors. I'm still using the rule for addition, but I just make a new vector called negative B that I can add these 2 vectors. So of course, if you have more than 2 vectors, okay, you're going to just repeat the same process until all vectors are included. Okay, you can get the new vector. And then another rule, the third rule we make is this. Sometimes we multiply a vector by a scalar, a pure number. Okay, so in that case, if you multiply a vector by a pure number, say if I have vector A, I want to make another vector 2 times A. Well, what do you do with this? you're gonna multiply the magnitude of A by this number, okay? That's gonna be the new magnitude of this new vector, okay? So say, I'm still using the same notation I use on the lecture. Let's call this a C, okay? So the magnitude of this C is gonna be 2 times the A, which is intuitive, right? You multiply vector by 2, okay? Of course, you're gonna multiply the magnitude by 2. And the direction has 2 options, okay? If this number is positive, okay, you're gonna draw this new vector in the same direction, right? So that's intuitive. You multiply by a positive number, you're not changing the direction. And then, if you multiply this number, say I call it, say another vector D, right? I want to do like 1/2 A or negative 1/2 A. So this is still A vector. How do I find that vector? Well, that vector, first of all, the magnitude is just going to be 1/2 of that. That's intuitive. I'm multiplying a vector by 1/2. The length is going to become 1/2. The direction, because I multiplied by negative 1/2, so the direction is going to be opposite to the original vector. So that's how I would draw vector D. So I hope that's intuitive. Because this law is intuitive to me, very intuitive, okay? More intuitive than this addition rule, okay? So that's how we multiply a vector by a scalar or a number, because a scalar is just a number, right? Okay, so that's how we add vectors, subtract vectors, and multiply a vector by a pure number, okay? So, but if I want to know this new vector precisely, okay, this is not the best way to do that, right? I don't want to draw these vectors because when I draw them, it's not going to give me very accurate result, right? You know, it totally depends on my drawing, okay? So there's another way, a better way to work with vectors when you add them or subtract them. That's a component method we discussed earlier. So I can always write this vector in components, right? If I have this vector, I know that I can break them into x components, 4 meters in x direction, 3 meters in y direction. So our notation is this, okay? Our notation is this. If this vector, okay, say R, or whatever, let's just still use A. So this vector is A, right? So I want to write it in component form, right? So, well, if I write it in words, I would say 4 meters in x direction and 3 meters in y direction, right? So that's how I specify the components of this vector, okay? Say this is this new vector A, this vector A. Now, but that's a lot of words to write, right? As physicists, we don't like writing a lot of words. We like symbols, okay? We like to simplify things. So we use some notation, okay? So one notation is this, okay? So we write it as 4 meters. So instead of writing in x direction, let's just use a symbol to present these 3 words so that we agree on this symbol. So every time I talk to you, I write something to you, I use this symbol, you understand, oh, that symbol means in x direction, right? As long as we agree on the same notation, okay? So one notation is this I hat and J hat, okay? So some books use this notation, and that's the notation I use in this class. So they use an I, that they put this symbol on top of the I, they call it I hat, okay? It's like this I is wearing a hat. They use this to represent these 3 words, okay? If this is the first time you see this notation, don't freak out. We're going to have a lot of notations in physics. The reason? Well, we just don't want to write a lot of words when we do things in physics, when we do math, especially when we do math. Then what about in y direction, okay? Then we use J with the hat on top of it, okay? So whenever you see I hat and J hat in this class, they just mean whatever this number is, that's the component in x direction. Whatever this number is, that's a component in y direction. They're just notations, right? Instead of writing so many words, we agree that, okay, now from now on, everyone just writes I hat and j hat instead of in x direction, in y direction, okay? We're gonna agree with that. That's our code. So every time we see this I hat and j hat, everyone knows what we are talking about, okay? So that's a notation. All right, so that's going to be a general way to write a vector, right? If I have a vector A, I'm going to break it into x and y components, so I can always write it this way, in general, right? The x component of A in front of I hat, the y component of this A in front of j hat. So when I see this, I know, oh, you just mean it has this component in x direction. It has this component in y direction. Okay, different books use different notations. I've seen notations like this. I've seen x hat and y hat in some books. I've also seen EX. This is also a widely used notation. EX with an arrow on top of it, and then EY with an arrow on top of it. Okay, so these are the common notations you would see in books, okay, different books. But again, as long as I know what this notation means, okay, so I know I don't need to write out these three words, okay. Whenever I see these notations, I know what this notation means. I'm just going to use this notation, okay. All right, so that's the notation we're going to use in this class, I hat and j hat, okay. So of course, if you have another vector b, and you can find the x component and y component, so you will write it this way, right? Bx I hat plus by j hat. So when I see this notation, I know, oh, you just mean it has a component in x direction, this component. It has a component in y direction with this number, okay? So then, once you have these two vectors in component form, adding, subtracting them, very easy, okay? Because you just work with components. You just add or subtract components, literally. Okay, so for example, if I want to add a plus b vector, I don't like drawing these vectors and use this hat tail method to draw the new vector, right? I just do this. Add all these x components together. That's going to give me a component in x direction, a new component. That new component is the x component of this new vector. Okay, and then I will get ay plus by j hat. Okay, so that's how I add two vectors. So if I call this vector, right, still r, right? So this number, you add them together, it's going to be the rx, right? So this is going to be equal to rx, and this is going to be equal to ry. Okay, so now you see that's how I'm going to get the new vector. And then if you still want me to draw this vector, I would just draw these two components on a coordinate system and then find the vector for you using a trick, using this right triangle. Okay, so that's how we add or subtract vectors, okay, algebraically. And that's very nice because you're just doing algebra with these numbers, right? You don't even need to draw anything, okay? But one thing I need to emphasize is that you can only add x components together, y components together, and of course z components together if we go to 3 dimensions, but we're not going to do that in this class. You can never add x component to y component, right? You never do like ax plus by in this class, so this is definitely wrong. Doesn't matter what you're finding in a problem. You never do this. This doesn't make any sense, okay? Because they're totally independent. You never do this. And of course, if you want to subtract these two vectors, you just subtract these two components, right? So you will get this component form of another vector. Say I want to find c vector equals a minus b, right? I'm just going to subtract all these vectors. So I would just get ax minus bx. That's going to be I hat, the new component of this c vector. And then ay minus by j hat. Okay? So that's going to be the new component for c in x direction. That's going to be the new component for c vector, the new vector in y direction, y component. Okay? So you see that it's much nicer to use components. Okay? So that's what we're going to do when we see vectors. When you see vectors, remember this. Always work with components, because you can never work with these vectors directly. They have magnitude and direction, and you don't work with them directly because you can't. It's not intuitive. It's not two numbers. Okay, you use components, then you're working with numbers. Okay, you just work with all the numbers in x direction, all the numbers in y direction. And of course, if you want to multiply a vector with a number, okay, so all you need to do is just multiply the x component with that number. That's going to give you the new x component in x direction. You multiply the y component with that number, right? So it's much nicer than working when drawing these vectors pictorially. And of course, if you go to 3 dimensions, so the only difference that you would have another component, and then usually we call it z component, and the symbol we use in this notation, we use k hat. So this I hat, j hat, k hat, they are called unit vectors in x, y directions. Why are they called unit vectors? Because the magnitude of this vector, these 3 vectors, is only 1. Okay? So that's why they're called unit vectors. Okay? So the magnitude of this vector is 1, and the direction of I hat is just in x direction. Direction of j hat, y direction. Direction of k hat, z direction. Right? Take a look at the coordinate system on the last slide. Okay, slide 18. All right? So that's what we're going to do when we see vectors. Always work with components. Okay? Now we have finished the theory. We're going to take a look at a real problem. So we're going to see how we can use the theory we learned, and also we're going to see why the displacement, as I said, the displacement concept we defined earlier, it's a very useful concept in real life. Okay? That is why we defined that. Okay? Now we're going to move on to PowerPoint 3. Take a look at this question. A hiker begins a trip by first walking 23.5 kilometers southeast from her car. She stops and sets up her tent for the night. On the second night, she walks 41.6 kilometers in a direction 60 degrees north of east. Okay, good. At which point she discovered the Forest Rangers Tower. Okay, so that's that. Now, what do we want to find? The first part. Find the components of the hiker's displacement on the first day. So let's draw it out. So the problem already sets up the coordinate system for us. So we can just use that coordinate system. But you can always set your own coordinate system, right, if the problem doesn't give you. So we're going to just use where she starts the trip as the origin. Okay, so that's where the car is, right? So the first day, she's going to walk 23.3 kilometers southeast from her car. So that's going to be the first trip I draw, right? If I want to draw a vector to present her trip on the first day, that's what I would do. Now we just want to find the components of this displacement on the first day and this x and y coordinate. Okay, this x, y coordinate system. So how do I find x and y components? Well, first of all, you're going to draw these components, right? So break this into x and y, make a projection to x. So that's how I'm going to draw the component. And also I'm going to draw an arrow to remind me that the component in that way in x direction, not in this way, right? And then I can also draw this component, right? I project it onto y-axis. So this is going to be, if I call this vector A, this is going to be ax. This is going to be ay. Okay? Now we're going to find the numbers, right? That's how we draw them, but I still need to find the numbers. How do you find numbers? That's when you use trick. That's when you make use of right triangles, okay? So the problem says this. On the first day, she walks 23.5 kilometers. So that means this length is 23.5 kilometers, right? That's the magnitude of this vector we just drew. What is the direction? Southeast, okay? Southeast, that means if I pick an angle here, like this angle, that's gonna be 45 degrees, right? So this guy has a length, 23.5 kilometers, and this is 45 degrees. Or if you pick the other angle, you still get 45 degrees, right? So it doesn't really matter which angle you use. You're always gonna get the same answer, okay? Okay? Because the physics doesn't depend on like what angle you pick, right? You just do the math, you will get the same answer. Now in this case, how do I find these two components? I can say make use of this angle, right? So how do you find ax? Ax, in this case, it's gonna be whatever this hypotenuse is, right? Which is 23.5 kilometers. Times, if I want to use this angle, 45, ax is adjacent to this angle. So that's going to be cosine, right? If I want to find ax, cosine 45 degrees. Okay? Now you do the same thing for ay. You do this number now times, now this ay is also this side, right? So if I want to find this side, the magnitude of this side is going to be the hypotenuse times sine this angle. Okay? So that's going to be the length of each component. Okay? But then you should be careful. This x component can be in this direction and this direction. Y component can be up and down or down, right? How do we distinguish that? Okay, in physics, how do we distinguish that in our math? Because I know that if it's a component up, if someone walked this way, it's totally different than walking this way. And if someone walks this way, it's totally different than walking that way. How do we distinguish that? We use signs, okay? So this guy is to the right, and this guy is up. In this coordinate system, but again, we don't write words in physics. We don't write words when we do math. What do? We use signs to distinguish them. Okay, so in this case, because I draw the x-axis to the right, that's usually people draw, right? So in this coordinate system, this is going to be positive to me. So if I get a component in that direction, I would call it negative. So then if I tell you the component with the correct sign, you know what I mean. You know the length of this component. You also know the direction of this component, right? So very clear, okay? I don't need to write any words. What about this guy, okay? So if this is how I draw y-axis, I'm assuming up is positive, right? This is origin. So anything down, how do I describe it, all right? I would just put a negative sign in front of it, okay? So if we all agree that I call up positive in y direction, so I tell you something has a component negative 5 meters in y direction, you know, oh, you mean a component 5 meters, but down, right? So that's how we do things in physics. We use signs, right? We use math, okay? We don't write a lot of words. So I don't need to write these words, you see? I'm just going to do this, okay? And then I tell you these two components, you know all the information about this vector. You can also draw this vector on your own if you don't have this, right? All right? So now you can put these numbers in your calculator and find these components. So, and then you can find the answer. Okay? So what is the right answer? This guy is going to give you 16.6 kilometers, right? This is going to give negative 16.6 kilometers. So this A vector, if I want to write it, right, I write it this way. 16.6, right? I hat, and then 16.6, negative 16.6 J hat kilometers, right? If you know what I hat means, what J hat means, what negative sign means, I show you this, you know everything about this vector, okay? Very clear, okay? That's why we use symbols in physics, right? We don't write a lot of words. So that's the first part. Now the second part, the hiker wants to return to her car after the trip. Find the shortest distance she can go, okay? So let's see. How do I find the shortest distance she can go? Well, let's first find the shortest distance. So she's gonna make this trip on the first day, and then on the second day, remember, she doesn't stop here, right? On the second day, she's gonna walk another 41.6 kilometers in a direction 6 degrees north of east. So if I draw that, so she's gonna start from here, okay? She's gonna walk another 41.6 kilometers in that direction, right? And then the angle, it says 60 degrees north of east. So you start from east, you go 60 degrees to the north. That's what it means. Okay? So she's going to end up here after the second day. And then she wants to go back to her car. What is the shortest distance? Well, we know the shortest distance is a straight line. Okay? So if I want to draw the shortest distance, that's how I would draw it for you. Right? So she's going to go this way, then she's going to, go the shortest distance back to her car. Okay? Okay? So that's how I draw it. But I want you to tell me that. I want you to tell me the number. That's when you do math, right? You see that I can't even tell the distance, even if I know how to draw that, right? I can't tell you the distance. You would have to use equations to do math, right? In order to make precise predictions, in order to make numerical predictions. That's what we do in physics, right? We don't do everything quantitatively. We don't do things intuitively. We want to make very precise predictions. That's why we use equations. We use math, okay? So that means that how do I find this distance, okay? That's when you make use of the vector analysis, these rules we set for the vectors, okay? Then you can just do math to find the shortest distance. Now you see that if I have this vector A here, and I call this vector B, and I draw A, B this way. So think about this. I have a vector A here. I'm going to draw vector B starting from the tip of A, and then I'm going to connect the starting point A to the tip of B. This vector, oh, that's the definition of A plus B, right? That's how we define that. If I call this R vector is just going to be A plus B. Right? You see that we're making use of this theory we just learned. So that means I just need to find the magnitude of this vector. How do you find the magnitude of this vector? Well, if I have the components of this vector, I would just do this, x squared plus y squared, right? Then find this magnitude. How do I find the x and y components? Oh, that's when we use the component form, right? Remember, if you want to add these two vectors together, you just add all the x components together. You add all the y components together. Then you just get the component for this x component of this sum, the new vector, and the y component of this vector, right? So I already have the x and y for A component. So all I need to do is just do the same thing, find this component for B vector and then add these two numbers together. That's going to become Rx. And add these two numbers together, literally, right? That's going to give me Ry, right? Then once I have the x and y, I would just do x squared plus y squared, right? And that's going to be the magnitude of this vector. And the magnitude of this vector is the shortest distance she can go to get back to her car, right? So this, what is this vector? We have a name for that. That's the displacement from A to B, right? So that's why you see that these vectors, the things we define, they are useful in real life. In this case, I would just say find the displacement, the total displacement of this hiker in these 2 days. That's the vector we just drew, okay? So now, okay, so let's do that. So I already have the components for A, right? So now the next thing I would do, find the components of B, okay? So what I would do is this, draw a new coordinate system. Don't draw everything on this original diagram. You're gonna make it so messy. You don't even know what you're doing, okay? I would draw another coordinate system, x and y. I would draw this vector again, starting from the origin. Remember, you can always move the vector parallel to another point. It's the same vector, doesn't change. So if this is the B vector, I would break it into x and y by doing the same thing, right? So this is going to be bx and has a direction. And then this is going to be by, right? If I project it into y direction, I would get this component. This is by. Bx and by. That's how you find the components. Once you have the components, you can add them. You can do this. Then you can find the magnitude of this new vector, which is the shortest distance. Okay? And then how do you find these components? Do we know? Look at this right triangle. If you have the hypotenuse and an angle, you can always find the other two sides. I do know that, right? This is 41.6 kilometers. What is the angle? The problem says this angle is 60 degrees, right? 60 degrees north of east. Now you see that you have this length, you have this angle, you can definitely find bx and by using trig. Once you found that, you can add them together to get this x and y. Then you do x squared plus y squared. Okay? And now you can pause the video, do the algebra, and see if you can get the number right. Okay? So let's see. So the bx in this case is going to be this side, right? This side, if I use this angle in the hypotenuse, I would still get 41.6 times 41.6 times cosine 60 degrees. Now again, take a look at the direction. We need to use a sign to distinguish left and right, up and down. It is to the right, it is in the positive x direction, so this is positive. I'm not going to assign a negative sign. What is this value? This is 20.8. Okay, that's the number I got. You do the same thing for by. So by, it's going to be this guy. Now I'm trying to find this side, right? This side equals this side. So that's going to be opposite to 60. Sine 60, right? So this number, again, take a look at the direction. This is the y component. It's up. So it is positive in this coordinate system. So I'm not going to assign a negative sign. So this is going to be 36. All right, so now I can put them in. This guy is 20.8. This guy is 36. Okay, now you can add them together, right? So you add them, you're going to carry these signs. You don't drop these signs, right? This is 16.6 plus 20.8. So what do you get? 16.6 plus 20.8, 37.4. That's the x component of this sum. Now you do the same thing here, right? So you get negative 16.6 plus this. You don't drop this negative sign, right? So you're actually doing 36 minus this. It's going to give you 19.4. Okay? So that means this vector is going to have an x component, 37.4, 19.4 y component. What is the magnitude, right? You're just going to do x squared plus y squared and then square root, right? What is the answer you got? You square this thing plus that and then square root. Okay, so the number I got is 42.1 kilometers. That's the answer, right? So the shortest distance she can go is going to be 41.2 kilometers back to her car. Okay, this is this part. Now the last part of this question, find the direction she should go for the shortest distance. Okay, that's the direction. She should go this direction. Okay, how do you describe that? Okay, you need to describe that very precisely. How do we do that? We use an angle, right? We use an angle. We pick some reference axis, and then we use an angle. So in this case, I want to use an angle, but this is just the opposite to that vector, right? So you see that this r vector, I can find this angle. So let's redraw this coordinate system. So at least I can find this angle theta, right? How do you find this angle theta? Well, we just found the x and y components. So if I want to find this angle, I would just use this Rx. So now this is Rx, right? This is Rx, and what is the number we found? 37.4 kilometers. What is Ry? Ry is the projection onto y. So this is Ry, right? What is Ry we found? 19.4 kilometers. Okay? So take a look at this right triangle. There's one, the big one. Okay? Now we can even erase this a and b. We don't need this a and b anymore, right? Once I find this new vector. Right? So take a look at this right triangle. If I want to find the theta angle, I will just do tan inverse this side over this side, which is a y over x. Okay? So I can put these two numbers to find the theta angle. But how do I describe the direction she should go? She's not going that direction, she's going this direction. How do you describe that direction using that angle? If I draw this r inverse for you, this is negative r. So she's actually going in negative r direction. Remember, she wants to go opposite to this displacement, right? This is the displacement from the car to the destination. But she wants to go that way. That's the definition of negative r. So if I draw this negative r for you, so it's going to be definitely opposite to that direction. How do you describe a direction that way? If this angle is theta I found, this is going to be a theta angle, right? So if this x and y coordinate, I would say it has an angle theta below negative x direction, then you know what I mean, right? So in this case, but if you want to describe that by using words, so you're going to figure out which one is the right answer. Okay? So first of all, you're going to find this angle, put these numbers in your calculator, you should get 27.4 degrees. That's the angle I found. And then again, if this is a free response question, you can just say, you can just draw it here and tell me the angle is 27.4, then I know what you mean, right? And then this, which right answer? Which is the right answer? This is actually south of west, if you want to say that in words. You start from west, you go to south, 27.4 degrees. That is the direction of negative r. No, this is not r. And that is the direction she wants to go, right? She wants to go in this direction. That's how I describe that direction, okay? So this south of west, south of east, sometimes these words are confusing, right? Some people don't even know how to describe that using south of west, south of east. That's what I usually say. You don't use words in physics, right? If this is a free response question, I'm not going to say it's the south of east, or I'm going to draw this out and then find this angle and just tell you it has an angle theta with this negative x direction. Or I'm just going to show you this angle and then this number. You know exactly what I mean. I don't need to describe that in words if it's a confusion to me, okay? So see that if you do math, everything is very clear, okay? So that's what we want to do in this class, okay? We used the vector theories, okay? In a real life problem, we found the shortest distance, we found the direction, okay? And we also used this concept, displacement, okay? Okay, that's why it's useful in real life. So I'm gonna stop here for this lecture.